Spin is everywhere. Every planet, every star, every galaxy, every atom, all of it rotating.
And yet, for most of human history, we treated spin as little more than a background detail.
Something things just happen to do.
It turns out that rotation is not cosmetic. It is not incidental. Spin is one of the most consequential physical properties in the universe, and when objects rotate fast enough, the consequences become genuinely extraordinary. The fabric of space itself begins to move. The rules governing light and energy bend in ways that should not be possible. Stars defy the physics that created them. Dead stellar remnants pulse across the galaxy with a precision that surpasses atomic clocks. And deep beneath our feet, churning rivers of liquid iron are spinning the magnetic cocoon that makes life on Earth possible. Take spin away, and the universe as we know it ceases to function. Understand it deeply, and some of the most puzzling phenomena in astrophysics suddenly begin to make sense. This is a story about what happens when things spin very fast, and also what happens when they spin slowly, and what happens when something that should have stopped spinning long ago simply refuses to. Let us start at the extreme end. There are objects in the universe that are so massive, so compact, and rotating so rapidly that they literally drag the surrounding fabric of space along with them.
Not metaphorically.
The actual geometry of space-time in their vicinity is pulled into rotation, the way a spinning drill bit pulls a thread of wood shavings along in a corkscrew behind it. These objects are rotating black holes, and their behavior at the boundary between what is possible and what is not possible is one of the strangest things general relativity predicts. Most people understand black holes through the concept of the event horizon, that invisible spherical boundary where the escape velocity equals the speed of light. Cross the event horizon and nothing comes back. Not particles, not radiation, not information. The event horizon is the point of no return, and everything inside it is, for all practical purposes, cut off from the rest of the universe forever. But what most popular accounts of black holes leave out is that the event horizon is only the innermost of several important boundaries around a black hole. For a black hole that is spinning, and essentially all real black holes do spin because the stars that collapse to form them were themselves rotating, there is an outer boundary even larger than the event horizon. This outer boundary is called the ergosphere, and the ergosphere is where physics starts behaving in ways that feel entirely wrong. The word ergosphere comes from the Greek word ergon, meaning work, and the name is deliberate because the ergosphere is a region from which energy can theoretically be extracted. But before we get to that extraordinary possibility, we need to understand what the ergosphere actually is and why it exists at all. When any massive object moves through space, it does not just passively sit in the pre-existing geometry of space-time. It distorts that geometry, mass-curved space. This is the fundamental insight of general relativity, and it is why objects follow curved paths in gravitational fields. They are actually following the straightest possible lines through a curved geometry. But the mass does something subtler than this as well. When a massive object rotates, it does not merely curve the surrounding space-time, it drags it. The spinning mass pulls the surrounding geometry into co-rotation with it, the way a spinning ball sitting in thick liquid would gradually pull the liquid around it into circular motion. In general relativity, this effect is called frame dragging, or by its more technical name, the lens-thirring effect. And for ordinary objects rotating at ordinary speeds, it is extraordinarily small. The Earth's rotation produces a frame-dragging effect that our most sensitive gyroscopes can just barely detect. For a black hole spinning at a substantial fraction of the speed of light, frame-dragging becomes something altogether more dramatic. In the ergosphere of a rotating black hole, the dragging of space-time becomes so extreme that it is impossible for any physical object to remain stationary relative to the distant stars. No matter how powerful an engine you had, no matter how much thrust you could generate, The rotation of space-time itself would carry you around the black hole in the direction of the black hole's spin. You cannot hold still in the ergosphere any more than a leaf floating in a river can hold perfectly still relative to the riverbank. The current simply carries it. In the ergosphere, space-time is the current, and the current cannot be fought. Near the event horizon at the inner edge of the ergosphere, this effect becomes even more extreme. At that boundary, the frame dragging is so powerful that space-time itself is being dragged at exactly the speed of light in the direction of the black hole's spin. This is a remarkable statement. It means that an object sitting at the boundary of the event horizon of a maximally spinning black hole would need to travel at the speed of light just to remain stationary from the perspective of a distant observer. And since nothing with mass can travel at the speed of light, nothing can remain stationary at that boundary. Every physical object must move with the spin of the black hole. There is no choice. Now here is where something important needs to be clarified, because the obvious question is, does this not violate the cosmic speed limit? Does this not contradict Einstein's own statement that nothing can travel faster than light? The answer requires a careful distinction that is easy to miss. Einstein's prohibition on faster-than-light travel applies locally. It applies to motion through space, measured by a local observer in a local reference frame. What frame dragging produces is not motion through space, but rather motion of space itself. The frame of reference is moving, and moving frames of reference can, in principle, recede from each other at any speed. This is not a loophole or an approximation. It is a fundamental feature of general relativity. The rule is that nothing moves faster than light through its local space-time. Space-time itself is not constrained by that rule. This same principle applies on cosmological scales, which is why distant galaxies in an expanding universe can be receding from us faster than the speed of light without violating any physical law. The space between us and them is expanding. They are not moving through their local space-time faster than light. They are stationary in their local frame, and the frame itself is moving. The ergosphere of a rotating black hole demonstrates this same principle operating at an extreme but local scale. But the ergosphere is not just a theoretical curiosity. It has a practical implication that is genuinely astonishing. In 1969, the mathematician and physicist Roger Penrose described a mechanism by which energy could be extracted from a rotating black hole, not from inside the event horizon, but from the ergosphere itself. The Penrose process, as it became known, works through a thought experiment that is deceptively simple. Imagine sending an object into the ergosphere of a rotating black hole. Because the object is inside the ergosphere but outside the event horizon, it is not necessarily doomed to fall into the black hole. It can, in principle, escape. Now, if the object splits into two pieces inside the ergosphere, and one piece falls into the black hole while the other piece escapes, the escaping piece can actually carry away more energy than the original object had when it entered. It is not getting energy from nowhere. It is extracting rotational energy from the black hole itself. The black hole slows down very slightly and the escaping fragment flies away with more kinetic energy than was put in. The numbers involved are staggering. Theoretical calculations show that the Penrose process could, in principle, convert up to 29% of the rest mass energy of the infalling material into kinetic energy of the escaping fragment. To put that in perspective, nuclear fission, with the process that powers nuclear reactors and atomic bombs, converts roughly 0.1% of rest mass into energy. Thermonuclear fusion, the process that powers the sun, converts about 0.7% of rest mass into energy. The Penrose process, at its theoretical maximum, converts 29%. It is by a wide margin the most energy-efficient process that general relativity permits. If you could feed a kilogram of matter into the ergosphere of a rotating black hole and capture the Penrose fragments, you would release energy equivalent to 29% multiplied by the speed of light squared multiplied by 1 kilogram. The speed of light is roughly 299,792,4 458 meters per second. Squaring that number and multiplying by 0.29 gives an energy output that dwarfs anything achievable through nuclear means by several orders of magnitude. Of course, the nearest known black hole to Earth is somewhere in the range of 3,000 light-years away, and the ergospheres of real astrophysical black holes are typically small enough, and the gravitational gradients near them are typically extreme enough, that any spacecraft venturing into the ergosphere would need to contend with tidal forces that would shred it apart long before any useful energy extraction could occur. And most large black holes are surrounded by enormously hot accretion disks, rings of infalling gas and dust that have been heated to millions of degrees as they spiral inward at near-light speeds. Navigating through that environment is not something within the reach of any foreseeable technology. So the Penrose process remains, for now, a thought experiment and a theoretical result rather than a practical energy source. But it reveals something deeply important about the universe, that space-time itself is a reservoir of energy, that the rotation of a massive object encodes vast amounts of extractable energy into the geometry of the space around it, and that in principle a sufficiently advanced civilization could tap that reservoir. There is also a more astrophysically realistic version of the Penrose process that operates in nature without any need for spacecraft or deliberate engineering. When rotating black holes are surrounded by magnetic fields, which they typically are, courtesy of their accretion disks, a related mechanism called the Blandford-Znajek process can convert the rotational energy of the black hole into electromagnetic energy. This is now thought to be the primary driver behind some of the most energetic phenomena in the observable universe, relativistic jets. These are narrow beams of plasma and radiation that shoot out from the poles of rotating black holes at velocities approaching the speed of light, sometimes extending for millions of light-years into intergalactic space. The jets from the black hole at the center of a galaxy called M87 extend for roughly 6,000 light-years. The energy powering those jets is, at root, the rotational kinetic energy of a black hole that has been spinning in some cases for billions of years. Spin, it turns out, powers some of the most spectacular light shows in the universe. Now consider the different categories of black holes, because the physical parameters involved vary enormously depending on what you are looking at. The smallest class, micro black holes, would have masses comparable to that of our Moon, roughly 7.35 times 10 to the power of 22 kilograms. All of that mass would be compressed into a region only about 0.2 millimeters in diameter, a point smaller than the width of a human hair, containing something as massive as the Moon. Moving up the scale, stellar black holes form from the gravitational collapse of massive stars. A typical stellar black hole has a mass roughly 10 times that of our Sun and a diameter of approximately 60 kilometers. These are the most common type of black hole and the best understood, because we can observe the supernovae that produce them and study the binary systems where a stellar black hole orbits a companion. Star-intermediate black holes occupy a mass, range between roughly 1,000 and 100,000 solar masses, too massive to have formed directly from a single stellar collapse, and not massive enough to be the supermassive black holes at galactic centers. Their formation channel is not fully understood. They may form through the merger of multiple stellar black holes in dense star clusters, or through the collapse of very massive stars in the early universe. And then at the top of the scale are the supermassive black holes that reside at the centers of most large galaxies. These range from 100,000 to many billions of solar masses. The one at the center of our own Milky Way, known as Sagittarius A star, has a mass of approximately 4 million suns. The one at the center of M87 has a mass of roughly 6.5 billion suns. And there are records, the most massive black holes known, called ultramassive black holes, exceed 40 billion solar masses. All of these objects, across this enormous range of masses share the same three fundamental properties: mass, electric charge, and angular momentum. Mass determines the size of the event horizon and the strength of the gravitational field. Charge creates an electromagnetic field around the black hole that attracts oppositely charged matter and repels like-charged matter. And spin, angular momentum, creates the ergosphere, the frame dragging, and the capacity for the Penrose process. These three numbers fully describe a black hole. No other information about the matter that fell in to create it can be retrieved from the outside. Whatever was swallowed, the chemical composition of stars, the genetic information encoded in biological molecules, the histories of entire civilizations that might have fallen into a sufficiently large black hole. All of it is reduced, from the perspective of the external universe, to three numbers. At the heart of each black hole lies what we call a singularity, though this term should be understood as a description of where our mathematics breaks down, rather than a confident statement about what physically exists there. For a non-rotating black hole, the singularity is a single point where, according to classical general relativity, the density becomes infinite and the curvature of space-time becomes unbounded. For a rotating black hole, the geometry is different. Rather than a single point, the singularity of a rotating black hole is a ring, a closed loop in space. This ring singularity opens up geometrically bizarre possibilities. In the idealized mathematical solution describing a rotating black hole, known as the Kerr metric after New Zealand mathematician Roy Kerr, who derived it in 1963, geodesics, the straightest possible paths through the curved space-time, can in principle thread through the ring singularity and emerge into regions of space-time that are mathematically separate from our own. These include regions where closed time-like curves exist, paths through space-time that loop back and intersect the past. The grandfather paradox looms. These features of the Kerr solution are taken seriously by relativists as mathematical results, but almost certainly do not reflect physical reality. The classical solution breaks down when quantum effects become significant at length scales near the singularity, and we do not yet have a quantum theory of gravity that can tell us what actually happens there. This brings us to one of the deepest unsolved problems in theoretical physics: reconciling general relativity with quantum mechanics. General relativity describes gravity as the curvature of space-time by mass and energy, and it does so with extraordinary precision on large scales. Quantum mechanics describes the behavior of matter and radiation at microscopic scales, and it too has been confirmed to extraordinary precision across an enormous range of experiments. But the two theories are fundamentally incompatible with each other in their mathematical foundations, and the region near a black hole's singularity, where both theories must apply simultaneously, is a place where this incompatibility becomes unavoidable. String theory, loop quantum gravity, and several other theoretical frameworks have each proposed ways to merge the two descriptions. But none has yet produced a complete experimentally confirmed theory of quantum gravity. The singularity at the center of a black hole is, in this sense, a giant signpost pointing at the deepest unsolved problem in fundamental physics. With that grounding in black hole physics, we can now follow the thread of spin to a different kind of object and a different kind of puzzle. Betelgeuse is a red supergiant star in the constellation Orion, visible to the naked eye on winter evenings and one of the largest stars known in our region of the Milky Way. If it were placed at the center of our solar system, it would engulf everything out past the asteroid belt, and its outer atmosphere would nearly reach the orbit of Jupiter. It is enormous by any reasonable measure. It is also, according to measurements published by the ALMA collaboration, spinning far faster than any star of its size and mass should be capable of spinning. The measurement itself exploited a phenomenon called the Doppler effect, the same effect responsible for the familiar change in pitch of a passing siren. When a source of waves is moving toward an observer, the waves arrive compressed, shifted to shorter wavelengths. When the source is moving away, the waves arrive stretched, shifted to longer wavelengths. Sound waves from approaching ambulances sound higher pitched because the wave crests arrive more frequently than they would from a stationary ambulance. The identical physics applies to light. Light from a source moving toward the observer is shifted toward the blue end of the spectrum. Light from a source moving away is shifted toward the red end. This optical Doppler shift is extremely small at ordinary speeds, far too small to notice with human senses, but for objects moving at kilometers per second, the shift becomes measurable with modern spectrographs. When a star is rotating, one limb of its surface is moving toward the observer while the opposite limb is moving away. The light from the approaching limb is blue shifted. The light from the receding limb is red shifted. The gradient of shifts across the stellar disk tells astronomers both the direction of rotation and the rotation speed at the equator of the star. For Betelgeuse, even though it is so far away, roughly 650 light-years, that ALMA's image of its disk is barely more than a blur, the Doppler color gradient across that blur was measured and analyzed. The result was a surface rotation speed of approximately 5 kilometers per second. Compare that to the constraints imposed by angular momentum conservation. Our Sun rotates at about 2 kilometers per second. Betelgeuse is roughly 1,000 times the volume of the Sun and somewhere between 10 and 20 times its mass. Angular momentum, like linear momentum and energy, is conserved in the absence of external torques. When a rotating object expands, its rotation rate must decrease by the square of the ratio of its radius. If you take a sphere rotating at 2 kilometers per second and expand its radius by a factor of 10, making it 1,000 times larger in volume, the equatorial velocity drops by a factor of 100, from 2 kilometers per second to 2 centimeters per second. If Betelgeuse formed from a star with the Sun's rotation and simply expanded to its current size, its rotation speed should be in the range of a few millimeters per second, not 5 kilometers per second. The measured value exceeds the predicted value by roughly 2,500 times. Whatever is happening, it is not simple adiabatic expansion of a normal stellar core. The stellar cannibalism hypothesis provides a physically coherent explanation. In a binary system, when one star begins to expand during the red giant phase, its outer layers can overflow the Roche lobe, the gravitational potential surface that defines the zone of gravitational dominance for each star, and fall onto the companion. But the reverse can also occur. The gravity of the larger star can pull material from the companion directly. In either case, the transferred material brings angular momentum with it. If Betelgeuse accreted a significant portion of a companion star's mass over its lifetime, it could have accumulated enough angular momentum to spin at its currently observed rate. The companion, stripped of much of its mass, might have been reduced to a white dwarf or neutron star, now orbiting invisibly within or near the supergiant's extended outer atmosphere. This scenario is not merely speculative, stellar. Cannibalism is observed in other systems and is thought to explain the anomalously rapid rotation of certain classes of stars known as blue stragglers in stellar clusters. But the alternative interpretation, that the apparent rotation is a measurement artifact produced by surface convection, cannot yet be ruled out. Betelgeuse's convective surface is extraordinarily turbulent. Detailed simulations of its atmosphere reveal convective cells spanning tens to hundreds of millions of kilometers, each rising and falling at speeds up to 30 kilometers per second. The surface at any given moment is a mosaic of upwelling and downwelling plumes, each Doppler shifted relative to the observer, depending on whether they happen to be moving toward or away from us. The random spatial distribution of these convective patches could, at a given moment, happen to produce a color gradient across the disk that mimics the smooth gradient expected from solid body rotation. And crucially, when the limited resolution of ALMA's observations is factored into simulations of this turbulent surface, the simulated blurred images produce a false rotational gradient consistent with the observations in approximately 90% of simulated cases. The turbulence is not just a minor source of noise, it is a dominant source of apparent rotational signal in low-resolution observations, distinguishing between true rotation and convective. Turbulence requires either much higher angular resolution than ALMA currently provides, or long-time series of observations that can separate the slowly evolving rotational pattern from the more rapidly changing convective features. Higher signal-to-noise observations using ALMA are already being analyzed, and theorists expect that the answer will emerge from those data over the next few years. Until then, Betelgeuse presents the unusual spectacle of a star whose most basic rotational properties remain genuinely uncertain. Is it a stellar cannibal spinning at thousands of times its natural rate? Or is its surface simply so turbulent that it is fooling the best telescopes in the world into seeing rotation that is not there? Both possibilities are fascinating, and one of them must be true. From the ambiguous rotation of a supergiant star, let us move to the even more perplexing rotation of a compact dead star, or something that looks like one. In 2022, a team using the Murchison Wide Field Array in Western Australia announced the detection of a remarkable radio signal. The signal arrived at Earth every 21 minutes and 58 seconds with extraordinary regularity. It was polarized in the characteristic manner of emission from rotating neutron stars. It exhibited sudden 90-degree rotations in its polarization direction, a feature that is considered a diagnostic hallmark of pulsar emission. Everything about its electromagnetic signature said pulsar, but the rotation period said otherwise. Normal pulsars rotate between several hundred times per second, for the fastest millisecond pulsars, down to about once per second for the slowest. The slow end of the distribution reflects the evolutionary fate of pulsars. As they radiate energy, they spin down, eventually becoming too slow and too weak to sustain the emission cascade that powers their lighthouse beam. The boundary below which pulsars can no longer emit is called the pulsar death line, and it is typically reached by the time the rotation period extends to several seconds. A period of 1300 seconds, 22 minutes, is more than 1,000 times longer than any known actively emitting pulsar. It is so far beyond the death line that by every existing theoretical framework, the source should be dark. To understand why the death line exists, we need to trace the emission mechanism from its source. Near the magnetic poles of a neutron star, the extraordinarily intense magnetic field, billions to trillions of times stronger than any field generated on Earth, accelerates electrons along the field lines. As these electrons curve along the field lines, they emit photons. At the right angles and energies, these photons can be spontaneously absorbed by the quantum vacuum and transformed into electron-positron pairs. Those pairs in turn emit photons of their own, which create more pairs in a runaway cascade that exponentially multiplies the number of charged particles and photons emanating from the pole. This pair production cascade is what gives pulsars their intense emission. The cascade ends when the photon energies drop below the threshold needed to create new pairs. The result is an intense, narrow beam of electromagnetic radiation directed along the magnetic poles, sweeping through space as the neutron star rotates. Because the magnetic poles of a pulsar are rarely aligned with its spin axis, the beam sweeps like a lighthouse, and an observer in the beam's path sees a flash once per rotation. For this cascade to operate, the magnetic field must be strong enough and the rotation must be fast enough to sustain the required energy injection. When the pulsar slows below a critical rotation rate, the electromagnetic power available at the poles drops below the threshold for pair production, and the cascade cannot be sustained. The pulsar goes dark,
This is the death line?
For standard pulsar magnetic field strengths, the death line falls at rotation periods of a few seconds. For GPM J183910, with a period of 1300 seconds,
It should have crossed the death line eons ago. The astronomers who discovered the signal
searched the historical data archives and found that the signal had been arriving with the same period since at least 1988, a span of 35 years of continuous archival evidence. More remarkable still, the period had remained essentially constant over that entire span. The pulsar-like interpretation requires that the source is spinning down as it radiates, and the rate of spin down tells you the magnetic field strength. The spin down rate for GPM J183910 is so small that it cannot have decreased its period by more than 0.28 milliseconds over 35 years. This stability is extraordinary. It implies that if the source is a neutron star, it is barely radiating energy at all relative to its rotational reservoir, yet it is producing electromagnetic emission detectable across 18,000 light-years of intervening space. These two facts are deeply contradictory. The possibility that it could be a magnetar, a neutron star with an exceptionally strong magnetic field, capable of generating bursts of emission through starquakes in its crystalline crust, was considered and rejected. Magnetar outbursts are powerful but transient, lasting months to years at most, not decades. And magnetar activity produces detectable X-ray emission. No X-rays have been detected from the position of this source. A highly magnetic white dwarf was proposed as an alternative, but the most radioluminous known white dwarf pulsar falls short of this source's intensity by approximately 9 orders of magnitude. Binary interactions between stars or brown dwarfs, interactions between a star and its orbiting planets. Each of these possibilities was evaluated and found inadequate, either by orders of magnitude in luminosity or by incompatibility with the polarization signature or the temporal behavior. The conclusion drawn by the discovery team was that GPM J183910 is either an extreme edge case of known physics, pushed far beyond any previously observed parameter range, or the first known example of an entirely new type of rotating compact object. The discovery team also noted that because this signal was found by searching archival data with parameters specifically designed to find slow period emitters, parameter, space that previous searches had largely ignored, similar objects likely exist throughout the galactic plane, their signals hiding in survey data that was never analyzed with sufficiently long period sensitivity. The universe may be populated with slowly rotating radio emitters of unknown type, all quietly pulsing away while human technology remained tuned to the wrong timescales. That thought is simultaneously humbling and exciting. Before leaving the subject of rapidly spinning stellar remnants, we should spend time with Geminga, a pulsar that earned its name partly because it spent decades successfully hiding its true nature from astronomers. Geminga was first detected in 1972 by NASA's Small Astronomy Satellite 2, which identified an unresolved source of gamma-ray emission in the direction of the constellation Gemini. The instrument was not precise enough to determine the source's exact location, and so the radiation's origin remained unidentified. Giovanni Bignami, an Italian astrophysicist who would dedicate much of his career to studying this enigmatic source, coined the name Geminga in 1976, a portmanteau of Gemini and gamma ray, and simultaneously a pun in Bignami's Milanese dialect meaning it is not there. In 1983, a weak X-ray signal was identified from Geminga using the Einstein X-ray satellite. The position was still imprecise, but the search area narrowed. Then, in 1991, 2 separate missions, the German Rosat satellite and the NASA Compton Gamma Ray Observatory, simultaneously detected pulsed emission from Geminga, and the mystery resolved. The source was pulsing with a period of 0.237 seconds just over 4 times per second in both X-ray and gamma-ray wavelengths. Geminga was a pulsar. Specifically, it was the third known gamma-ray pulsar after the Crab and Vela pulsars. And unlike those predecessors, it was nearly radio silent, emitting nothing detectable at the frequencies that radio telescopes conventionally searched. This radio silence was puzzling because pulsars were canonically radio emitters. Their discovery by Jocelyn Bell in 1967 had come precisely through radio telescope observations. A pulsar that did not emit significantly in radio wavelengths challenged the assumed universality of pulsar emission. The resolution, when it came in 1997 through observations by the Pushchino Radio Astronomy Observatory, was that Geminga was emitting in radio wavelengths, just at a much lower frequency than typically searched, peaking around 100 MHz rather than the 430 to 1600 MHz range used by most surveys. The interstellar medium attenuates low-frequency radio signals more strongly than high-frequency ones, further weakening the already faint signal. Geminga was not truly radio silent. It was radio quiet at the frequencies anyone had been listening to. There is also a geometric explanation for Geminga's anomalous behavior. Pulsar radio emission is narrowly beamed along the magnetic poles. Gamma-ray emission comes from a broader disk-like region around the spin equator. Whether an observer sees radio pulses, gamma-ray pulses, both, or neither depends on how the pulsar is oriented relative to the line of sight. Comparisons between Geminga and a nearby pulsar known as B0355 plus 54 illustrate this clearly. Both pulsars are roughly the same age and spin at similar rates. But Geminga is seen primarily in gamma rays with almost no radio emission, while B0355 plus 54 is one of the brightest known radio pulsars and is invisible in gamma rays. The explanation is orientation. Geminga's spin equator faces Earth while its radio poles sweep past at angles that miss us. B0355 plus 54 points. Its radio poles almost directly at us, while its gamma-ray equator sweeps in directions that bypass the solar system entirely. The same object at a different orientation would present entirely differently to our telescopes. What makes Geminga particularly significant for modern astrophysics is the enormous halo of high-energy gamma rays surrounding it. For decades, Geminga was known to produce gamma rays from its magnetospheric emission, the cascade process near its poles. But the full extent of the emission surrounding the pulsar was not appreciated until a team led by astrophysicist Matteo Di Mauro analyzed a decade of data from the Fermi Large Area Telescope, published around 2022. By carefully subtracting all other gamma-ray sources from the dataset, they revealed a vast, glowing halo extending dramatically beyond what anyone had expected. At an energy of 10 billion electron volts, the halo spans 20 degrees of sky, similar to the area of sky covered by the Big Dipper. At lower energies, it is larger still. If human vision extended into the gamma-ray band, Geminga's halo would dominate the night sky, covering an area 40 times the apparent size of the full moon. This halo is produced by the pulsar's rotation. As Geminga spins 4 times per second, its intense magnetic field accelerates electrons and positrons to near the speed of light. These particles stream away from the pulsar and interact with ambient photons from starlight and the cosmic microwave background, transferring energy to those photons through a process called inverse Compton scattering and boosting them to gamma-ray energies. The resulting cloud of high-energy radiation extends for tens of light years around the pulsar and continues to grow as the pulsar emits more relativistic particles. The size and luminosity of this halo allowed Di Mauro and her team to calculate that Geminga alone could account for as much as 20% of the excess positron flux detected near Earth by the Alpha Magnetic Spectrometer. That instrument, known as AMS-2, has been mounted on the International Space Station since 2011, roughly 200 meters above Earth's surface in a position shielded from most of the atmospheric effects that complicate ground-based measurements. In its first years of operation, it recorded more than 400,000 cosmic ray positrons, the single largest positron dataset ever assembled, representing a 100-fold increase in the world's positron data at that time. The abundance of positrons was greater than predicted by standard models of cosmic ray production and propagation. For several years, some physicists speculated that this excess might be a signature of dark matter annihilation. Dark matter particles, if they exist, might occasionally collide with each other and annihilate, producing electron-positron pairs as products. If enough dark matter annihilation events were occurring in the galactic halo, the resulting positrons might show up as exactly this kind of excess in the AMS-2 data. The Geminga finding substantially weakens that dark matter interpretation, though it does not rule it out entirely. A single pulsar 800 light-years away can apparently account for a fifth of the excess, simply through the ordinary operation of its spin-powered particle acceleration. If other pulsars throughout the galaxy contribute similarly, the entire excess can plausibly be explained without invoking dark matter at all. The mystery of the positron excess, which was once considered a potential window into the nature of dark matter, may turn out to have a far more prosaic explanation. Rotating stellar remnants showering the galaxy with high-energy particles through the same basic physics that has been understood since pulsars were first discovered. Now, let us expand our perspective from individual rotating objects to the largest structures in which rotation plays an organizing role: galaxies. The apparent visual form of a spiral galaxy, those sweeping arms extending from a bright central bulge, is so iconic that it defines how most people picture a galaxy. But the rotational dynamics underlying that structure are not at all obvious from the image. The first and most fundamental point is that spiral galaxies are not solid objects rotating like wheels. They are gravitationally bound collections of hundreds of billions of individual stars, each following its own orbit around the galactic center under the collective gravitational influence of all the other stars, plus the gas, dust, dark matter, and the central supermassive black hole. The orbital period of a star depends on how much mass is enclosed within its orbit and how far it is from the center. Stars near the center, enclosed within a smaller mass distribution and closer to the gravitational potential well, orbit with shorter periods than stars at large radii. If spiral arms were material structures, if the stars in the arms were permanently embedded in the arm and swept around with it, then a problem arises. The inner parts of the arm orbit faster than the outer parts, so the inner ends of the arms would continuously outpace the outer ends, winding the arms tighter and tighter over time until they completely wrapped around the galactic center and disappeared. Over the time that galaxies have existed, billions of years through hundreds of galactic rotations, any material arm would have wound into invisibility long ago. This is the winding problem, and it has been recognized as a serious obstacle to simple models of spiral structure for more than half a century. The most widely accepted solution involves density waves. In this model, the spiral arms are not material concentrations of stars at all. They are regions of enhanced gravitational potential, density perturbations in the galactic disk, that rotate through the galaxy more slowly than the stars themselves. Stars on their individual orbits approach the density wave from behind, slow down as they enter the region of enhanced gravitational pull, pile up temporarily, and then accelerate back out the far side. The arm appears bright because stars and gas pile up in it, not because the same stars are always there. The density wave is to the galaxy what a traffic jam is to a highway. The jam can propagate backward, while the individual cars move forward. Individual particles pass through the structure, while the structure itself persists. The density wave pattern can maintain a stable two-armed or multi-armed geometry over billions of years without winding up, because it is the wave that rotates slowly, not the individual stellar orbits. The density wave picture receives a striking analogy from Saturn's ring system. At certain locations in Saturn's rings where the orbital period of a ring particle is in a simple numerical ratio with the orbital period of one of Saturn's moons, a resonance. The moon's periodic gravitational kicks accumulate coherently and drive the ring into a tightly wound spiral density wave. These structures are visible in detailed Cassini spacecraft images as closely spaced brightness variations in the rings, looking like the grooves of a vinyl record. They are not material ridges. They are density perturbations propagating through a population of independently orbiting ring particles sustained by the resonant gravitational forcing. The same mathematics that describes these ring waves, scaled up by many orders of magnitude, describes the spiral arms of galaxies. But density waves do not explain everything about galactic structure. A competing contribution comes from local processes. Supernova explosions and the intense radiation from massive young stars generate shock waves in the surrounding gas, triggering the compression that leads to new star formation. This positive feedback can amplify local density enhancements and help maintain arm structure, even in regions where the large-scale density wave is weak. The two mechanisms, density waves from large-scale gravitational perturbations and local self-propagating star formation triggered by stellar feedback, are not mutually exclusive and probably both operate in real spiral galaxies to varying degrees depending on the galaxy's environment, merger history, and the distribution of mass. The link between galactic rotation and dark matter was established through painstaking observational work in the 1960s and 70s, when astronomers mapped the rotational velocities of stars and gas, clouds at different distances from the center of a spiral galaxy, using Doppler shifts to convert wavelength offsets into line-of-sight velocities and triangulating the three-dimensional
velocity field. They can compare the measured
rotation curve with what Newtonian gravity predicts given the observed distribution of luminous matter. The prediction is that rotation velocities should rise steeply near the center, where the enclosed mass grows rapidly with radius, then decline as radius increases beyond the bulk of the visible matter. The same behavior that characterizes the planets of the solar system, with Mercury orbiting fastest and Neptune slowest. What is actually observed is a rotation curve that rises steeply in the center, flattens out at an intermediate radius, and then remains essentially flat, constant velocity all the way out to the edge of the detectable gas disk and often beyond. Stars and gas at the outer edges of spiral galaxies orbit at essentially the same velocity as stars at much smaller radii. For this to be consistent with Newtonian gravity, there must be a large amount of unseen mass distributed throughout the galaxy, especially in the outer regions. The mass profile required to produce a flat rotation curve is an extended spherical or spheroidal halo with a density that falls off as approximately the inverse square of the radius. This halo extends far beyond the visible disk of the galaxy and dominates the total mass budget. The luminous matter, the stars and gas that can be seen with telescopes, contributes only a small fraction of the total gravitational mass. The rest is dark matter, interacting gravitationally but not electromagnetically, and its distribution is inferred from how it affects the rotation of everything else. The rotation curves of galaxies change over cosmic time. When we observe very distant galaxy whose light
has been traveling for billions of years and therefore
shows us these galaxies as they were
billions of years ago, because we see rotation curves that
differ from those of nearby galaxies. Stars in ancient, distant galaxies rotate somewhat more slowly in the outer regions than comparable stars in nearby galaxies today. The most natural explanation is that dark matter has been concentrating toward galactic centers over cosmic time, increasing the gravitational influence at intermediate radii and accelerating the outer stellar orbits. By looking at galaxies at different distances, and therefore different epochs in cosmic history, we are watching the long-term evolution of galactic rotation in real time, seeing how the interplay of dark matter, baryonic matter, and mergers has shaped the rotation curves we observe today. There are peculiar exceptions that further illuminate the complexity of galactic dynamics. The galaxy NGC 4622 is a spiral galaxy that rotates in the direction its leading arms point, which is the opposite of the more common configuration. Rather than spiral arms that trail behind the rotation like streamers blown backward by the wind of forward motion, this galaxy's arms point forward into the direction of rotation. The standard explanation for this configuration involves a past galactic merger or encounter in which the orbital angular momentum of the infalling material was anti-parallel to the spin of the original galaxy, reversing the net rotation direction. The Messier 64 galaxy, sometimes called the Black Eye galaxy because of the distinctive dark dust lane across its inner disk, presents an even more dramatic anomaly. Its inner disk of stars and gas rotates in one direction. Its outer disk of gas rotates in the opposite direction. Strikingly, the stars in the outer disk do not share the counter-rotation of the outer gas. Only the gas moves retrograde. The favored explanation is a past merger with an extremely gas-rich companion galaxy whose orbital direction was opposite to the rotation of the original galaxy. The infalling gas from the companion settled into a retrograde orbit because of its initial counter-rotating angular momentum, while the stellar populations were largely unaffected because stars interact gravitationally but not hydrodynamically, passing through each other without the dissipative collisions that force gas clouds to settle into equilibrium orbits. Rotation preserves memory of gravitational history. A galaxy's current spin state is a palimpsest, layered with the signatures of every major merger and accretion event across billions of years of evolution. All of these celestial
Examples of rotation, from black holes to pulsars to
galaxies, share a common physical foundation with a rotating system that is far more immediate to our daily existence. The liquid iron dynamo inside the Earth. The Earth's magnetic field is not a permanent feature of the planet, like its mass or its average density. It is continuously generated by the motion of electrically conducting fluid in the outer core, and it depends critically on the rotation of the Earth to maintain its coherent, organized structure. The outer core is a shell of liquid iron and nickel surrounding the solid inner core, extending from roughly 2,900 kilometers below the surface to roughly 5,100 kilometers below the surface. The temperature at the boundary between the inner and outer core is approximately 6,000 degrees Celsius, comparable to the surface temperature of the Sun. The temperature decreases as you move outward through the outer core toward the mantle above. This temperature gradient drives convection. Hot material from the deeper regions rises toward the cooler mantle boundary, cools, and then descends again, creating the circulating flow that generates the Earth's magnetic field. But convection alone would produce a chaotic, disorganized magnetic field. Many small field regions pointing in different directions, cancelling each other out on large scales. The Earth's rotation organizes this chaos. As the convective plumes rise through the rotating outer core, the Coriolis effect, the same pseudo-force that causes cyclones to spiral counterclockwise in the northern hemisphere, deflects them into helical spiraling paths. These helical flows are the key. A conducting fluid moving in a helical path generates a magnetic field that adds coherently to a large-scale dipolar pattern, with field lines entering at one magnetic pole and exiting at the other. The result is the familiar global dipole that has oriented compasses toward magnetic north for as long as human civilization has relied on compasses for navigation. The dynamo process is described mathematically by the equations of magnetohydrodynamics, a set of coupled partial differential equations describing the simultaneous evolution of fluid velocity and magnetic field in a conducting medium. These equations are nonlinear and chaotic, which means that even very small differences in initial conditions can lead to dramatically different long-term behaviors. The Earth's dynamo is essentially a turbulent magnetohydrodynamic system, and like all turbulent systems, it exhibits complex, irregular fluctuations superimposed on its average large-scale behavior. These fluctuations manifest observationally as the continuous migration of the magnetic poles, the variable intensity of the geomagnetic field over time, and the occasional dramatic reorganizations known as geomagnetic excursions and reversals. The North Magnetic Pole has not stayed still since scientists first located it in 1831. It has migrated approximately 1,100 kilometers from its original position in northern Canada, tracking northward and westward toward Siberia. Its rate of migration has also increased from roughly 16 kilometers per year in the early 20th century to approximately 55 kilometers per year in recent decades. This acceleration reflects changes in the pattern of core convection beneath the geographic North Polar region, where a broad region of the outer core appears to have undergone some reorganization in its flow pattern over recent decades. Whether this migration will continue at its current rate, accelerate further, or reverse direction cannot be reliably predicted with existing models. Over geological timescales, the fluctuations in the dynamo have occasionally grown large enough to produce full reversals, events in which the geomagnetic dipole collapses and then rebuilds with opposite polarity, so that what was magnetic north becomes magnetic south. The geological record of these reversals is preserved in the remanent magnetism of igneous rocks. When lava erupts and cools through the Curie temperature, the temperature below which the magnetic domain structure of iron-bearing
minerals becomes fixed.
The minerals record the ambient magnetic field at that moment. Subsequent geological activity can preserve these magnetic records for hundreds of millions of years. By analyzing the magnetic orientations of successive layers of volcanic rock, geologists have reconstructed a detailed timeline of geomagnetic polarity. The result is a sequence of polarity epochs punctuated by reversals, with the long-term average spacing between reversals being approximately 450,000 years, though with enormous variability. Some consecutive reversals are separated by only tens of thousands of years. Others are separated by millions. One period in the Cretaceous, known as the Cretaceous Normal Superchron, saw no reversals for approximately 40 million consecutive years. The Kierman reverse superchron, spanning from roughly 312 million to 262 million years ago, saw 50 million years of stable reverse polarity. The causes of these variations in reversal frequency are not understood. The current geomagnetic situation is noteworthy by the standards of geological history. The last reversal occurred approximately 750,000 years ago, at the end of what is called the Matuyama Chron. With a long-term average reversal interval of 450,000 years, we are overdue in a statistical sense, though as the record makes clear, the statistical average is not a reliable guide to when any particular reversal will occur. More concrete signs of possible impending change include the steady decline in global dipole field strength over at least the past 200 years of instrumental measurements, and the growth and apparent bifurcation of the South Atlantic anomaly. The South Atlantic anomaly is a region where the geomagnetic field at the surface is significantly weaker than the global average, covering a broad area centered roughly over the South Atlantic Ocean and the neighboring parts of South America. The weakness in this region is associated with a patch of reversed polarity in the outer core beneath it, a region where the magnetic field generated by the core is locally antiparallel to the dominant dipole direction, reducing the surface field in the overlying region. The anomaly has been growing since systematic monitoring began, and recent satellite data suggests it may be splitting into two distinct lobes. This behavior is qualitatively consistent with numerical simulations of geomagnetic reversals, in which the first stages often involve the growth and multiplication of reversed polarity patches in the outer core The practical consequences of a full geomagnetic reversal are difficult to quantify with confidence, partly because we have never observed one with modern instruments, and partly because the field evolution during a reversal is inherently chaotic and unpredictable in detail. What is reasonably certain is that the transition period, which can last from 1,000 to 10,000 years, would see the global field intensity drop to as low as 10% of its current value. During this period, the shielding provided by the magnetosphere against solar wind and energetic cosmic ray particles would be substantially reduced. Auroral activity currently confined to high latitude zones would extend to much lower latitudes. Satellites in low Earth orbit, already occasionally damaged or disrupted by solar energetic particle events during solar maximum, would experience chronically elevated radiation environments. The Hubble Space Telescope already shuts down certain instruments every time it passes through the South Atlantic anomaly on its orbital path. A globally weakened field would create South Atlantic anomaly-like conditions everywhere. The biological consequences are harder to predict. A 2021 study from the University of New South Wales examined the Lachamps geomagnetic excursion, which occurred approximately 42,000 years ago. This was not a full reversal, but rather a temporary excursion during which the field weakened dramatically and the poles moved far from their usual positions before the field recovered, a process lasting roughly 800 years. The team argued that the Lachamps event coincided with elevated atmospheric radiocarbon levels consistent with increased cosmic ray penetration during the field weakening, and that this forcing may have contributed to megafaunal extinctions in Australia. The affected species included Diprotodon optatum, the largest marsupial known to have existed, comparable in size to a rhinoceros. They included Procoptodon goliah, a short-faced kangaroo nearly 3 meters in height. They included the Thylacoleo carnifex, the marsupial lion. These were large, evolutionarily sophisticated animals that had persisted for hundreds of thousands of years. The timing correlation with the Lachamps excursion is intriguing, though establishing causation from correlation in the paleontological record requires care, and other factors. The arrival of modern humans in Australia around the same period, climate changes unrelated to the geomagnetic event complicate the picture. Looking at the broader geological record, it is notable that most geomagnetic reversals do not appear to coincide with mass extinction events. The record of polarity reversals over the past 83 million years tallies approximately 183 events, while the record of significant mass extinctions is far shorter. Life has survived the vast majority of reversals without any detectable perturbation. This resilience may reflect the fact that the atmosphere itself provides radiation shielding that does not disappear when the magnetosphere weakens. The ozone layer, which absorbs ultraviolet radiation, and the bulk of the atmospheric column, which stops lower energy charged particles, continue to function even during geomagnetic transitions. The field would need to drop to essentially zero and remain there for far longer than any known excursion or reversal transition for the atmosphere to be significantly eroded. NASA has noted that even a substantially weakened geomagnetic field would leave surface life protected to a significant degree. The greater risk is probably technological rather than biological. Our modern global infrastructure depends on satellites for communications, navigation, financial transactions, weather prediction, and monitoring of countless environmental parameters. Our electrical grids are vulnerable to geomagnetically induced currents during large solar storm events, and those events become more damaging when the magnetosphere provides less shielding. Our aircraft routes, particularly polar routes, may need to be rerouted to avoid elevated radiation during periods when the field is weakest. These are manageable challenges if they develop slowly enough to allow adaptation, and geomagnetic transitions, even at their fastest, unfold over centuries to millennia, which is slow by human standards. The challenge is that our technological civilization is only a few centuries old, and our critical infrastructure is only decades old. We have no experience operating it under a substantially different geomagnetic environment. Planning for such an environment is, for the moment, not a priority that has found its way into mainstream infrastructure policy. There is one additional observation that adds urgency to monitoring the geomagnetic situation. The South Atlantic anomaly, as noted, has been growing continuously since it was first systematically measured. More recent analyses of satellite magnetic field data suggest that it may be in the early stages of dividing into two separate lobes centered at different geographic positions. This morphological change is qualitatively consistent with numerical geodynamo simulations of what happens in the outer core in the centuries before a reversal begins. Whether this represents the actual onset of a reversal, another temporary excursion, or simply a long-period fluctuation that will eventually subside without a full polarity change, cannot be determined from current data. The geodynamo operates on time scales and in a physical regime that makes reliable long-range prediction currently impossible. What connects all of these phenomena, the ergosphere of a black hole, the anomalous rotation of Betelgeuse, the 22-minute mystery signal, the gamma-ray halo of Geminga, the rotation curves of galaxies? The geomagnetic dynamo is the physical quantity of angular momentum and its extraordinary tenacity. Angular momentum is one of the most conserved quantities in nature. Once imparted to a system, it persists until some external torque removes it. The Earth has been rotating for 4.5 billion years, and it will continue to do so for billions more, gradually slowing only through the tidal interaction with the Moon. A pulsar formed in a supernova explosion inherits the angular momentum of the collapsing stellar core, compressed into a sphere 20 kilometers across, and that angular momentum spins it up to hundreds of revolutions per second, rates that persist for millions of years before measurable slowing occurs. A galaxy inherits its angular momentum from the angular momentum of the molecular cloud that collapsed to form it billions of years ago, and the overall sense of that rotation is preserved through countless stellar generations. A black hole accretes the angular momentum of every particle that ever falls past its event horizon, storing it all in the geometry of the surrounding space-time, available to do work, to extract energy, for as long as the black hole exists, which may be longer than the current age of the universe. The laws of conservation that govern angular momentum are not arbitrary features of the particular physics of our universe. They reflect deep symmetries in the mathematical structure of space and time. According to Noether's theorem, one of the most profound results in theoretical physics, every continuous symmetry of the laws of physics corresponds to a conserved quantity. The conservation of linear momentum arises from the translational symmetry of the laws of physics. The laws are the same in every location. The conservation of energy arises from the time translation symmetry of the laws of physics. The laws are the same at every moment. And the conservation of angular momentum arises from the rotational symmetry of the laws of physics. The laws are the same in every direction. As long as the universe is rotationally symmetric, as long as there is no preferred direction built into the fundamental laws, angular momentum will be conserved. It cannot disappear. It can only be transferred from one system to another. This means that the rotation we observe throughout the universe is not accidental. It is not something that could be otherwise. It is the direct consequence of how angular momentum was distributed when the universe began, flowing from the primordial fluctuations that seeded galaxies and stars and planets, conserved through every generation of stellar birth and death, every gravitational collapse and merger, every supernova and accretion disk and magnetic dynamo. The spin of the Earth is part of an unbroken chain of angular momentum transfer stretching back 4.5 billion years to the rotating molecular cloud from which the solar system formed. The spin of a pulsar carries the angular momentum of a star that burned for millions of years and ended in a cataclysm. the spin of a black hole may preserve angular momentum for timescales longer than the current age of the universe. We are still uncovering the consequences of this universal rotation. Every year brings new observations that reveal new ways in which spin shapes the behavior of matter and space-time at scales from stellar surfaces to galactic halos. The 22-minute mystery signal reminds us that the parameter space of rotating objects has not been fully explored, and that new types of rotators may still await discovery in data we have already collected. The anomalous behavior of Betelgeuse reminds us that even nearby, intensively studied objects can present fundamental uncertainties when observations are pushed to their limits. The gamma-ray halo of Geminga reminds us that the long-term consequences of a pulsar's rotation extend far beyond the pulsar itself, shaping the particle environment of an entire region of the galaxy. The flat rotation curves of galaxies remind us that the dynamics of rotation have revealed the existence of a dominant component of the universe's mass that remains entirely unexplained, and the weakening of the Earth's magnetic field reminds us that the
rotating dynamo beneath our feet is not guaranteed.
It requires the right conditions to sustain itself. It has failed before temporarily, and it may fail again. When it does, the consequences will unfold slowly enough for human civilization to adapt, but only if we are paying attention. Only if we understand the physics well enough to anticipate what is coming, and only if we take seriously the possibility that the invisible, spinning currents of liquid iron 3,000 kilometers below the surface are among the most important phenomena in the history of life on this planet. If you found value in this exploration and want to keep following the science at its most interesting frontiers, consider subscribing. The universe has far more to show us. There is a peculiar irony in the fact that the most fundamental measure of how exotic a rotating black hole is, the spin parameter, denoted in general relativity as a lowercase a divided by the massum, is dimensionless. It ranges from 0 for a non-rotating black hole to 1 for a maximally spinning black hole. This number condenses an extraordinary amount of physics into a single ratio. A Kerr black hole with a spin parameter of 0 is described by the simple Schwarzschild solution discovered in 1916. A Kerr black hole with a spin parameter approaching 1 is an entirely different kind of object. Its ergosphere swells outward, growing in extent until at maximum spin, the outer boundary of the ergosphere at the equator extends to a radial distance twice the Schwarzschild radius. Its photon orbit split into prograde and retrograde paths with dramatically different energetics. Its innermost stable circular orbit, the closest point at which matter in an accretion disk can sustainably orbit before being swallowed, shrinks toward a minimum of half the Schwarzschild radius for a prograde orbit in a maximally spinning black hole, compared to 3 times the Schwarzschild radius for a non-rotating one. These numbers matter observationally because the material at the innermost stable circular orbit has a specific gravitational potential energy that depends on the spin. The energy released as matter falls from the outer accretion disk to the innermost stable circular orbit, converted into radiation by friction and magneto-hydrodynamic processes, depends sensitively on how close that orbit is to the event horizon. For a non-rotating black hole, roughly 6% of the infalling rest mass energy is radiated. For a maximally spinning black hole, that fraction rises to approximately 42%. This is why the X-ray emission from accreting black holes can, in principle, reveal the spin of the black hole. More luminous accretion for a given mass. Accretion rate means higher spin. Observational estimates of black hole spin have been attempted through several methods. The continuum fitting method analyzes the thermal X-ray spectrum of the accretion disk to infer the location of the innermost stable circular orbit. The ion line method analyzes the profile of fluorescent emission from ion atoms in the inner accretion disk, whose line shape is distorted by Doppler shifts and gravitational redshift in a way that encodes the space-time geometry near the horizon. Both methods have their systematic uncertainties, but when applied to stellar black holes in X-ray binary systems, they have yielded spin estimates suggesting that black holes can have a wide range of spin parameters,
from essentially 0 to values very close to 1.
The supermassive black hole at the center of M87, whose shadow was imaged by the Event Horizon Telescope collaboration and announced in 2019, has been estimated through various methods to have a spin parameter that may be relatively high, though the uncertainties remain large. The black hole at the center of our own galaxy, Sagittarius A star, imaged by the Event Horizon Telescope and published in 2022, also has spin estimates, though characterizing its spin precisely is an ongoing challenge given the turbulent and dynamically complex accretion environment around it. Measuring the spin of these objects is not a purely academic exercise. The spin of a black hole records its formation and accretion history in a way that no other observable property can. A black hole that formed from a rapid collapse with little subsequent accretion will retain the spin of the collapsing object. A black hole that has accreted a large fraction of its mass from a disk will have been spun up by the angular momentum deposited by that disk, and its spin parameter will approach one from below. A black hole that has experienced multiple mergers with other black holes, arriving at different angles and orbital configurations, will have had its spin modified by the angular momentum vectors of the merging black holes, potentially resulting in a spin parameter anywhere in the range from 0 to near 1, depending on the details. The gravitational wave signals detected by LIGO and Virgo from binary black hole mergers carry information about the spins of both merging black holes, encoded in the detailed time-frequency structure of the signal. As the catalogue of detected binary black hole mergers grows, more than 100 events detected as of the most recent observing runs, the statistical distribution of black hole spin parameters is beginning to constrain models of binary black hole formation and the environments in which they arise. One of the most dramatic observational consequences of black hole spin that has been confirmed in astrophysical systems is the relativistic jet. The Blandford-Zanajek mechanism, proposed in 1977 by Roger Blandford and Roman Zanajek, provides the theoretical framework. A rotating black hole threaded by a magnetic field connected to its accretion disk transfers angular momentum and energy to the magnetic field through the frame dragging effect. The magnetic field lines anchored in the disk and threading through the ergosphere are twisted by the differential rotation between the inner accretion disk and the slowly rotating outer disk. The resulting magnetic pressure gradient drives a relativistic outflow along the rotation axis of the black hole, a pair of jets moving in opposite directions at velocities very close to the speed of light. The energy source for the jet is the rotational kinetic energy of the black hole extracted through the electromagnetic coupling provided by the magnetic field. As the black hole loses angular momentum to the jet, its spin parameter decreases. Over very long timescales, a black hole that drives powerful jets will spin down, though the timescales are typically very long compared to the age of the universe for the most massive black holes. These jets are among the most energetic phenomena in the observable universe. The most powerful known jets, associated with the most luminous quasars in the early universe, carry kinetic power comparable to a significant fraction of the bolometric luminosity of the quasar itself, which is already thousands to millions of times more luminous than an entire galaxy of stars. When these jets propagate into the surrounding intergalactic medium, they heat it, push it aside, and drive enormous cavities in the gas halos surrounding galaxies. This feedback process, the injection of energy from the central black hole into the surrounding galaxy and its gas reservoir, is thought to be one of the primary mechanisms that regulate star formation in massive galaxies. When the jet feedback is strong enough, it heats the gas that would otherwise cool and collapse to form new stars, suppressing star formation and quenching the galaxy's growth. The spin of the central black hole, which controls how efficiently the Blandford-Znajek mechanism operates, therefore influences not just the immediate vicinity
of the black hole, but the evolutionary trajectory
of the entire galaxy in which it resides. The connection between angular momentum and structure formation in the universe runs even deeper than this. When the universe was much younger and denser, in the first few 100 million years after the Big Bang, the formation of the first stars and galaxies was shaped fundamentally by angular momentum. Quantum fluctuations in the density of matter in the very early universe, stretched to macroscopic scales by the rapid exponential expansion called cosmic inflation, seeded the density perturbations that gravitational instability would eventually amplify into galaxies and clusters. But the detailed structure of what formed, how massive the first clouds were, whether they formed single massive stars or clusters of smaller ones, how efficiently they converted gas into stars, how fast the galaxies spun, depended on the initial angular momentum distribution of these density fluctuations. The tidal torque theory of galaxy spin proposes that the angular momentum of a protogalactic cloud is acquired during its initial collapse phase through tidal interactions with neighboring overdensities before the cloud separates from the Hubble flow and turns
around to collapse on itself.
The torques from neighboring concentrations of mass impart a net angular momentum to the cloud, and this angular momentum is conserved through the subsequent collapse and star formation, eventually appearing as the overall rotation of the resulting galaxy. The statistical distribution of galaxy spins in the universe is therefore a tracer of the large-scale structure of matter at the epoch of galaxy formation. Surveys of galaxy spin alignments, whether neighboring galaxies tend to spin in the same direction, or whether galaxy spins are aligned with the large-scale filaments of the cosmic web, have the potential to constrain models of structure formation and the nature of dark matter. Recent surveys have found tantalizing but controversial evidence for large-scale coherent alignments of galaxy spin directions over scales of tens of millions of light-years. If confirmed, such alignments would place important constraints on the primordial power spectrum of density fluctuations and the processes that shaped the cosmic web during the first billion years of the universe. The rotation of galaxies in this view is not merely a local, dynamical property, but a fossil signature of the initial conditions of the universe and the subsequent history of gravitational interactions that built up the cosmic structure we observe today. Back on Earth, the practical relevance of spin does not end with the magnetic field. The Earth's rotation itself has shaped everything about the conditions for life. The diurnal temperature cycle, the circulation patterns of the atmosphere and oceans, the distribution of climatic zones, the Coriolis-driven circulation of weather systems, the tidal locking of large-scale atmospheric waves to the rotating planet.
Remove the Earth's rotation, slow it drastically,
as has happened to Mercury and Venus through tidal interactions with the Sun, and the climate consequences would be catastrophic for anything resembling the current biosphere. One hemisphere would bake continuously in uninterrupted sunlight, while the other froze in permanent darkness. The atmospheric circulation patterns that distribute heat globally would be replaced by a simple day-side to night-side convective cell. The oceans, if they persisted at all, would not recirculate on their current timescales. The magnetospheric dynamo would shut down as the convective driving from rotation ceased. The Moon plays a stabilizing role in this story as well. Through tidal interactions, the Moon slowly transfers angular momentum from the Earth's rotation to the Moon's orbit, causing the Earth to gradually slow its spin while the Moon recedes very slowly from the Earth. The current rate of slowing is roughly 1 millisecond per century added to the length of the day. Over the 4.5 billion years since the Moon formed, in the giant impact hypothesis, from the debris of a collision between proto-Earth and a Mars-sized impactor, this process has lengthened the Earth day from an original period of perhaps 6 hours to its current 24 hours. At the same time, the Moon has receded from an original distance of perhaps 15,000 kilometers to its current distance of roughly 384,000 kilometers. This recession is ongoing and measurable. Laser ranging experiments that bounce laser pulses off retroreflectors left on the Moon by Apollo astronauts have directly confirmed that the Moon is currently moving away from the Earth at approximately 3.8 centimeters per year. The Earth is losing angular momentum to the Moon-Earth orbital system at a measurable, quantifiable rate. There is also a subtler effect of the Moon's presence, the stabilization of Earth's axial tilt. Without the Moon's gravitational influence, computer simulations suggest that the Earth's rotational axis would undergo chaotic variations in its tilt relative to the orbital plane, swinging between nearly 0 degrees and more than 85 degrees on timescales of millions of years. Currently, the Earth's axial tilt oscillates between about 22.1 and 24.5 degrees over a period of roughly 41,000 years, a small, regular, predictable variation that contributes to the Milankovitch cycles of ice ages. A chaotically varying axial tilt would produce dramatically more extreme and unpredictable climate swings, potentially incompatible with the long evolutionary timescales required for complex life. The Moon, by its own orbital angular momentum interacting with Earth's rotation and axial precession, acts as a gravitational stabilizer. Remove the Moon and the Earth's axis loses its anchor, potentially making the climate history that allowed complex life to evolve impossible. The presence of a large Moon at the right distance, with the right mass, providing the right tidal torque. All of this traces back, ultimately, to a specific angular momentum configuration that arose from a chance collision 4.5 billion years ago. We have traveled, in this exploration, from the curved space-time around spinning black holes to the pulsating remnants of dead stars, from the slow dynamo deep within the Earth to the vast rotation curves of whole galaxies. At each level, the same fundamental property, angular momentum, the quantified measure of rotation, has proven central, consequential, and deeply connected to phenomena that range from the immediately practical to the philosophically profound. The magnetic field that protects the complex chemistry of living cells from solar radiation is a direct consequence of angular momentum conservation in the cooling Earth. The gamma ray halo that bathes a region of the galaxy in high-energy radiation for
hundreds of thousands of years after a
Pulsars formation is a product of angular momentum in the spinning neutron star. The relativistic jets that regulate the growth of whole galaxies are powered by angular momentum stored in the geometry of a spinning black hole. The spiral arms that make galaxies the spectacular objects they are the equilibrium patterns of a rotating gravitating disk. Nothing in the universe holds perfectly still.
Nothing ever has.
And in the universal restlessness of rotation, in the conservation of angular momentum across every scale from the quantum to the cosmological, we find one of the deepest symmetries that nature has so far revealed. That symmetry, the rotational invariance of physical law, has been tested in every experiment ever conducted. It has never been found to fail. It may be among the most fundamental truths we know about the structure of reality.
And every spinning star, every wheeling galaxy,
every pulsar ticking out its metronomic signal across the dark is another confirmation of it. Consider the neutron star more carefully, because it sits at an intersection of physics that is still actively being worked out. When a massive star exhausts the nuclear fuel in its core, the outward radiation pressure that has supported the core against gravitational collapse disappears. The collapse is catastrophic and takes less than a second. In that fraction of a second, the core, which may have been roughly the size of the Earth with a mass of about 1.5 times our Sun, collapses to a sphere roughly 20 kilometers across. This represents a density increase of roughly a factor of 10 to the power of 13. Conservation of angular momentum during this collapse drives a spectacular spin-up. If the core was rotating at a relatively modest rate before collapse, it emerges from the collapse rotating perhaps several hundred times per second. This is the pulsar birth spin, and it can be inferred from the properties of young pulsars in supernova remnants. The crab pulsar, the remnant of the supernova observed by Chinese astronomers in 1054, rotates approximately 30 times per second. It is less than 1,000 years old. Given its current spin-down rate, it was rotating much faster at birth. The Vela pulsar, older at roughly 11,000 years, rotates about 11 times per second. These young, fast pulsars are the brightest and most easily detected. As they age and spin down, they cross the death line and their radio emission fades. The total pulsar population of the galaxy includes billions of neutron stars across all ages and spin rates, but only those that are young enough and spinning fast enough to be above the death line are observable as radio pulsars. The rest are dead pulsars, dark, cold neutron stars drifting through the galaxy, invisible to radio telescopes. Occasionally, if a dead pulsar is in a binary system with a companion that fills its Roche lobe and transfers mass onto the neutron star, the accretion of angular momentum can spin the pulsar back up to rotation rates of hundreds of times per second, reactivating it as what is called a recycled pulsar or millisecond pulsar. These recycled pulsars are among the most stable rotating objects known. Their spin rates are so constant that they can be used to detect gravitational waves passing through the galaxy by monitoring tiny perturbations in the arrival times of their pulses. This application, called pulsar timing arrays, is now beginning to produce results. International collaborations monitoring arrays of millisecond pulsars have recently found evidence for a gravitational wave background, a diffuse hum of gravitational radiation permeating the galaxy, likely produced by the inspiral of supermassive black hole binaries in the centers of distant merging galaxies. The millisecond pulsar thus connects the physics of stellar rotation to the physics of gravitational waves to the physics of galaxy mergers. Rotation, once acquired, enables measurement at a precision that could not otherwise be achieved. The spinning neutron star becomes a gravitational wave detector. The spinning galaxy becomes a probe of dark matter. The spinning black hole becomes an energy reservoir that can power jets across millions of light years. The spinning liquid iron core of the Earth becomes the biological shield of an entire biosphere. None of this was anticipated when the conservation laws were first worked out. Newton did not know that angular momentum conservation would one day be exploited to measure gravitational waves. Faraday did not know that the rotating Earth's magnetic dynamo would be identified as a precondition for the evolution of complex life. Einstein did not know, or perhaps he suspected in the late years of his life, when the full implications of general relativity were still being worked out, that a rotating black hole would contain a region where energy could be extracted from pure space-time geometry. These discoveries emerged from the patient accumulation of observations, the construction and testing of mathematical theories, and the willingness to follow the physics wherever it led, regardless of how strange the destination turned out to be. The universe has a consistent property across all scales and all epochs. It does not hold still. The first subatomic particles that formed in the hot plasma of the early universe carried quantum mechanical angular momentum. The first atoms that assembled from those particles had electrons orbiting their nuclei. The first clouds of gas that collapsed under gravity in the early universe were seeded by fluctuations that carried angular momentum from tidal interactions with their neighbors. The first stars burned through their nuclear fuel and collapsed, imparting their angular momentum to their remnants. The first galaxies aggregated from rotating clouds and settled into rotating disks. And somewhere in this long chain of angular momentum transfer and conservation, specific configurations arose that made life possible. A planet the right distance from its star, rotating at the right rate to maintain a stable climate, with a liquid metal core rotating fast enough to drive a dynamo, protected by a large moon that stabilized its axial tilt and gradually transferred angular momentum to its orbital distance. The probability of this specific confluence of rotational properties might be extremely low, but in a universe vast enough and old enough, even very low probabilities can be realized. We do not yet know how many other planetary systems share the rotational properties that Earth has. We do not yet know whether the specific dynamo configuration of Earth's outer core is common or rare among rocky planets with metal cores. We do not yet know whether the presence of a large stabilizing moon is typical or exceptional. These are questions that planetary science, exoplanet surveys, and comparative planetology are beginning to address, but definitive answers remain years or decades away. What we do know is that here, on this rotating planet, orbiting a rotating star, embedded in a rotating galaxy, the specific values of various angular momenta conspired over 4.5 billion years to produce conditions in which matter became complex enough to study itself. To ask why everything is spinning, to work out the mathematics of frame dragging and pulsar emission and geodynamo theory, to detect gravitational waves using spinning stellar remnants as clocks, to image the shadow of a black hole and measure the geometry of the curved space-time around it. The questions that remain open are among the deepest that physics confronts. What exactly happens at the ring singularity of a rotating black hole when quantum gravity takes over from classical general relativity? What is the physical nature of the dark matter that dominates galactic rotation curves, and why has it so far evaded every attempt at direct detection? What is powering the 22-minute signal, and how many more objects like it are quietly pulsing in the archival data of radio surveys around the world? Is the current weakening of the Earth's geomagnetic field the beginning of a reversal that will profoundly affect our technological civilization? Or is it a temporary fluctuation that will reverse of its own accord? Is Betelgeuse a stellar cannibal spinning at an impossible rate, or a turbulent surface fooling our best instruments? These questions are not merely academically interesting. They are connected to each other by the thread of angular momentum, and answering them will require new instruments, new observations, and almost certainly new theoretical ideas that do not yet exist. The universe keeps spinning, and the science of spin keeps revealing new things about why the universe looks and behaves the way it does. Every rotation at every scale carries information about the history of the matter doing the rotating and the physical laws that govern it. Reading that information, patiently, carefully, with instruments that probe every available wavelength and every relevant timescale, is one of the central projects of 21st century astrophysics. The results, when they come, will be worth the wait. There is a deep conceptual tension running through all of this that is worth drawing out explicitly, because it has shaped the history of physics in ways that are easy to overlook. For most of classical mechanics, rotation was treated as something straightforward. An object spins, it has angular momentum. That angular momentum is conserved unless a torque acts on it. Simple, clean Newtonian. But when general relativity arrived, it became clear that rotation was far more consequential than anyone had realized. Mass does not just sit in space-time and curve it. A rotating mass drags space-time along with it in a way that produces physical effects, frame dragging, that have no analog in Newtonian gravity. The gravity of a rotating mass is not the same as the gravity of a non-rotating mass of equal magnitude, even far from the object. The geometry of space-time around a Kerr black hole is fundamentally different from the geometry around a Schwarzschild black hole, and those differences affect every geodesic, every possible path, in the surrounding space-time. This is not a small correction. It is a qualitatively different kind of physics, and recognizing it required accepting that rotation was not merely a kinematic descriptor attached to matter, but a geometric property woven into the fabric of space-time itself. The lens-Thirring effect, the ergosphere, the Penrose process, None of these would exist in a universe described by Newtonian gravity plus special relativity. They require the full machinery of general relativity, with its dynamic, curved, frame-draggable spacetime. The rotating black hole is the most extreme realization of this insight, but the principle applies at every scale. The rotation of the Earth, while too slow to produce ergospheres or frame-dragging detectable by anything except the most sensitive satellite gyroscopes, is fundamentally a general relativistic phenomenon expressed at the non-extreme end of the parameter range. Quantum mechanics adds yet another layer to the story of spin. At the quantum level, spin is not merely a description of an object rotating. Elementary particles, electrons, protons, neutrons, quarks, photons have intrinsic angular momentum called spin that does not correspond to any actual rotation of the particle. An electron has spin 1/2, meaning its intrinsic angular momentum is 1/2 times the reduced Planck constant. This spin is quantized. It can only take certain discrete values, not a continuous range. For an electron, the component of spin along any chosen measurement axis is either +1/2 or -1/2 in units of the reduced Planck constant. There is no intermediate value. This quantization of spin has profound consequences for the structure of matter. The Pauli exclusion principle, which states that no two identical fermions, particles with half-integer spin-like electrons, can occupy the same quantum state simultaneously, is directly responsible for the shell structure of atoms, the existence of the periodic table of elements, and therefore the entire edifice of chemistry. The intrinsic spin of electrons is also directly responsible for magnetic properties of materials. Each electron behaves like a tiny magnetic dipole with its north and south poles determined by the direction of its spin. In most materials, the spins of electrons in different orbitals are paired antiparallel, cancelling each other out, and the material is not strongly magnetic. In ferromagnetic materials like iron, exchange interactions between neighboring electrons favor parallel alignment of spins in large domains, producing the macroscopic magnetism that we experience in permanent magnets and in the iron minerals within the Earth's crust. The geomagnetic reversals recorded in volcanic rocks are preserved not through any macroscopic mechanism, but through the quantum mechanical spin states of electrons in iron mineral grains, frozen into alignment with the ambient field at the moment of crystallization. The record of planetary magnetic history is written in quantum spin. These quantum spins and their collective behavior underlie the electrical conductivity of metals, including the liquid iron of the Earth's outer core. The flow of electrical current, which is ultimately the flow of electrons, is the basis for the generation of magnetic fields in the core through Faraday's law of induction. Without the quantum mechanical properties of electrons, including their spin and the statistics that govern their collective behavior, the geodynamo would not function. The chain from fundamental quantum mechanics to planetary magnetism to biological evolution is complete. The discovery of quantum spin was one of the most surprising results of early quantum mechanics. When Wolfgang Pauli proposed in 1925 that each electron has an additional two-valued quantum number beyond its spatial quantum numbers, he could give no classical explanation for what it was or where it came from. He described it as a classically non-describable two-valuedness. George Uhlenbeck and Samuel Goudsmit a few months later proposed that this two-valuedness corresponded to a spinning of the electron on its own axis. An electron that was literally spinning, like a top. The proposal was immediately criticized on physical grounds. If the electron were a classical sphere of finite size with the known electron mass and charge, rotating fast enough to produce the observed magnetic moment,
its surface would be rotating faster than the speed of light, which is impossible.
Pauli himself told Uhlenbeck and Goudsmit not to publish because the idea was too obviously wrong. They published anyway. And the modern understanding is that quantum spin is a genuinely new kind of property with no classical analog, described by the mathematical framework of quantum mechanics rather than by any picture of literal rotation. Yet it produces angular momentum. It obeys the same conservation law, and it has consequences that range from the shell structure of the periodic table to the functioning of magnetic resonance imaging machines to the record of geomagnetic reversals locked in ancient volcanic rock. The concept of spin, which entered physics as a classically nonsensical emergency fix to explain spectroscopic anomalies, turned out to be one of the most fundamental properties of matter. The full picture that emerges from all of this is one in which rotation, angular momentum in all its forms, from the quantum spin of elementary particles to the angular momentum of supermassive black holes, is not a secondary feature of the universe, but a primary one. It shapes the structure of matter at the smallest scales through quantum statistics. It shapes the structure of atoms through electron orbital angular momentum and spin. It shapes the structure of stars through their birth in rotating molecular clouds and their evolution through angular momentum transport and loss. It shapes the structure of planetary systems through the conservation of angular momentum during protoplanetary disk formation. It shapes the properties of planetary magnetic fields through core dynamics driven by planetary rotation. It shapes the structure of galaxies through the conservation of angular momentum during their formation and through their response to dark matter halos. It shapes the most extreme phenomena in the observable universe through the properties of the Kerr metric and the Blandford-Znajek process. And it shapes our ability to probe the universe through the remarkable stability of millisecond pulsars and their utility as gravitational wave detectors. What will the next decade of observations reveal about spin and angular momentum? Several important advances are in progress or on the near horizon. The Square Kilometre Array, a massive next-generation radio telescope spanning sites in South Africa and Australia and combining the collecting area of thousands of individual antenna elements, will dramatically increase the sensitivity and time resolution of radio surveys, potentially revealing many more slowly rotating radio transients like GPMJ 183910 and helping to characterize the population of these mysterious objects. The next-generation Event Horizon Telescope, which will add new stations and observe at higher frequencies, will produce sharper images of the shadows of Sagittarius A star and M87, placing tighter constraints on their spin parameters and testing general relativity in the strong field regime. LISA, the Laser Interferometer,
Space Antenna,
gravitational wave detector in space planned for launch in the early 2030s, will detect the gravitational wave signals from the slow-in spiral of massive black hole binaries in the centers of merging galaxies,
measuring the spins of those black holes with unprecedented precision.
and continued monitoring of the Earth's geomagnetic field through satellite missions will provide a clearer picture of whether the South Atlantic anomaly is truly the precursor of a reversal or merely an unusually deep fluctuation. In the ongoing chaotic behavior of the outer core, these are not marginal refinements. They are potential revolutions in what we know about the behavior of rotating matter and space-time across every accessible scale. The history of observational astronomy is a history of instruments getting better, angular resolution improving, sensitivity increasing, and each improvement revealing things that were not visible before, sometimes confirming existing theories, sometimes discovering phenomena that required entirely new frameworks. There is no reason to expect this history to end. There is every reason to expect that the next generation of instruments will reveal new rotating objects, new angular momentum distributions, new consequences of spin that we do not currently anticipate and cannot currently predict. The universe, it turns out, has been trying to tell us something through the rotation of everything it contains. We are still learning how to listen, and so the story of spin is not finished. It is, in many respects, just beginning. We have the mathematical tools to describe the space-time geometry around a rotating black hole with arbitrary precision. We have instruments sensitive enough to detect the faint, polarized radio pulses of a neutron star rotating once every 22 minutes from 18,000 light-years away. We have satellites measuring the minute drift of the Earth's magnetic North Pole in real time. We have gravitational wave detectors registering the final in-spiral of two spinning black holes that merged more than 1 billion years ago. We have the geological record of every geomagnetic reversal for the past 83 million years, encoded in the quantum spin states of electrons in volcanic rock. And yet, confronted with a slowly pulsing radio source below the pulsar death line, we cannot say what it is. Confronted with a supergiant star whose rotation speed defies angular momentum conservation, we cannot yet distinguish between stellar cannibalism and surface illusion. Confronted with rotation curves that imply a dominant non-luminous mass component in every galaxy, we have not identified the particle responsible. The edges of understanding are still very much in sight. The next signal from the spinning universe may be the one that changes everything we think we know. Every observation we make, every signal we detect, every rotation we measure is a message from the cosmos encoded in angular momentum. Deciphering those messages is the work of astrophysics. It has no foreseeable end, and for that we should be grateful. The universe is not waiting for us to catch up. It keeps spinning, keeps radiating, keeps recording its own history in the angular momentum of everything it contains. Our job is simply to keep looking.